Hello and welcome back to Data Management with Stata from the University of Vermont program in Clinical and Translational Science. I'm Ben Littenberg. Today we'll do Module 3, Cleaning House, Preventing, Identifying, and Correcting Data Entry Errors. Here's the agenda for Module 3. Types of errors, preventing errors in data entry, identifying, correcting errors, how to use and detect duplicate records, and then we'll talk about your assignment. Open up Stata and follow along at home with Module 3, dataset.dta. What is an error? Two definitions. The first, a failure to complete a task as planned or to select the correct plan. Equivalently, you can think of an error as any action, choice, or decision that results in a product or service that is not suited for purpose. Psychologically, errors are due to either mechanical slips, such as striking the wrong key and getting a typographic error, lapses in attention and failing to notice that you have typed in or the wrong data or perhaps selected the wrong file from a drop list, mistakes in judgment, such as making a decision to use one particular programming approach rather than another programming approach, and then finally intentional violations of rules, which is knowingly skipping a step or otherwise introducing an error because you're prioritizing your personal situation over the goals of the project. For instance, you're in a hurry and want to get home sooner. Programming errors come in several types. The first major category are the typographical, grammatical, and logical errors that are fatal. In other words, Stata won't run. They're fairly easy to detect because Stata gives an error message in bright red. For instance, this command here, summarize, has a spelling error in it. There's supposed to be 2 M's, not just one. Let's go over to Stata and see when we type in summarize, we get back this error message about command summarize is unrecognized. And so the program stops and we know we've got a bug to deal with. Non-fatal errors are a little bit trickier. Stata will run, but the results will be incorrect. Sometimes these are very hard to detect. For instance, this command, generate BMI is equal to pounds divided by inches squared, up to the second power, divided by 703, the correction factor for imperial units, has a subtle error in it. And that error is that this division should be a multiplication. Let's type it into Stata and see what happens. Generate BMI is equal to pounds divided by height squared divided by 703. And I have a fatal error in there that I used height when I should have said inches. Okay, now let's summarize BMI. And we were expecting numbers between, say, 15 or 16 at the low end up to 50 or 60 at the high end. And what we see here is that the values run from this very small number of quadruple 02 up to triple 03. And these numbers are just way out of range for BMI. Clearly, we've made a mistake. And the mistake was with that division marker. So what I'm going to do is drop BMI. We'll talk more about the drop command in a minute. And then I'm going to use the page up command 3 times to find the previous erroneous line. And I'm going to click back with the left arrow key, backspace over the slash, and put in the multiplication sign. And since BMI doesn't exist anymore, I will now generated again. Now I will go up 3 page ups to recover that summarize BMI command I had. And now we're seeing a mean of 26 and a range from 14 to 177. Well, that's quite large, but it's still much more likely to be correct than the numbers we had before. Another category of errors is definitional. The data don't mean what you think they mean. Height is in inches. You thought it was in meters. Duration refers to time since diagnosis, not length of treatment. Does married include legally separated or civil unions? So all of these kinds of programming errors can be considered bugs. The term bug appeared in about 1945. The first person to use it in any kind of documented way was Grace Hopper, who was working on one of the early mechanical electronic relays, gigantic room-sized computers, and doing some of the very first computer programming. And at that time, she was, I believe, a young naval officer, later went on to become a rear admiral. And when one of the mechanical relays stopped working, she went to the back of the relay panel, relay number 70 in panel F, and found a moth stuck in the relay, an actual physical bug. And so she wrote it into her logbook, first actual case of a bug. And she was able to restart the machine and make everything happen correctly after that. More on debugging errors later in the course. Well, data entry errors can happen for a variety of reasons. Typographic errors such as omissions, insertions, replacements, reversals, and these can happen within a single entry of a variable within a record. They can also happen within variable names, within file names, system names, and command names. And so you can find them anywhere, and you got to keep an eye out for them. Cut and paste errors happen when spreadsheet and word processing programs, particular, when you cut a column or a row and paste it in the wrong column or the wrong row, and all the data are then off by one column, all the variables are off by one variable name. Blocks of rows, which are records, or columns, which are variables, are sometimes pasted twice, leading to duplicates. There's actually ways to make this happen in Stata also, but it's a lot easier to avoid. There are alternative ways to do it. So knowing the process by which the data got to you helps a lot. Understanding that it was first edited in some sort of spreadsheet and then sent to you gives you an opportunity to understand how it might have gotten rows and columns scrambled. How can we prevent errors? Well, the usual method of making sure everyone is trained well is critically important. Coming up with a good work environment with good lighting and minimum noise, few distractions, minimizing time pressure. Another method to prevent errors is to have research subjects enter their own data rather than have them fill out written forms and then require another step that can introduce yet another data entry error. Forms design, paper forms and computer screen forms should have unambiguous instructions, big blocks demarcated to write text entry into, plenty of room for folks who have sloppy handwriting, and if it's an embedded, if it's a paper form, put the key entry instructions right on the sheet next to where the data were hand entered. You can use forcing functions. This is a data software operation that insists on the legal values of the data and refuses to accept any that aren't in the legal range. And my favorite is automation. Get rid of the people completely and collect data directly from machines. For instance, laboratory test results are collected without retyping them or doing any sort of human handling of the data at all. Now, I'll note that these ideas apply before data analysis begins. Interpretation errors are going to happen after your analysis has run, and they're basically problems in misunderstanding your output. For instance, not understanding what the units of measurement were. Again, inches and meters will give you different results. Then there's statistical confusion. Clinical versus statistical significance is a well-known problem. A good understanding of confounding is very important for interpreting almost every kind of statistical work you get. And then there's program-specific variation in output. Each program has its own particular jargon and formats, abbreviations and shortcuts, and you need to understand what the output of your particular program looks like. Stata is no different in this regard. Let's talk about how to identify errors. One method is self-inspection by the data entry worker. And this is where you're typing along and you watch your own work as you go, or perhaps at the end of each block of entry, you go back and check. Now this catches a lot of errors, probably most errors, but not all of them. There's always a couple that get through, no matter how careful the data entry worker was. To approach this, a lot of people use post-entry inspection by another worker. First, I enter the data, and then as I'm typing it, or soon after, you go look at my results and match them up. Now, this is pretty time-consuming and costly because you need two people to do the work. Another approach is double data entry, where I enter my data, you don't look at my entry, you enter the data independently, and then we have some sort of method to compare the results. And then we have to resolve any discrepancies against the original source. This is very time-consuming and costly, but sometimes it's a reasonable thing to do. Note that you can't use this for subject self-entry as a rule. Post-entry analytic checks, and we're going to talk some about this in a moment, but that's where you look at the data distributions and the values that you have in your data set before starting your main analysis to look for problem cases. And then finally, analytic failures. The first clue to the error is that your results are wrong, as we saw with the BMI example. No one method will find all errors, so it's important to keep your antennae up and be ready to apply different methods. Well, let's take a look at the data themselves, inspect the actual data, so look before you leap. Commands to look at summary statistics for numeric values, we'll go over a couple of them. They each provide a slightly different look at the variable. In particular, what we want to do is look for missing values, and we want to check the range for outliers. It's also a good idea to look at the central tendency. One great method is a command called codebook, which you can then, after the codebook command, you can enter any variables, one or more that you like. Let's do that. Here's codebook, and then I'm going to enter patient ID and age. And what we see here is it printed out for patient ID, that's the variable name. Here's a label that's been assigned, capital ID. And we can see that it's a numeric value. Its range is 1 to 250. It's in ones. And there's 250 unique values with no missing values. So that's good. It looks like we've got a serial number from 1 to 250 with none missing. And that's exactly what I intended when I made up this variable, so that's good. Now age is not quite as clean because it's real, it's actually a variable characteristic, and it's again a numeric. Its range in this case is 15 to 125, but only 33 of those possible values are used. And none of them are missing. And again, it's in ones, in other words, to the nearest unit, in this case, probably years. We note that age is unlabeled. And here we get some more details that are kind of interesting. The mean age is 30.6. There's a standard deviation of 10.5. And here's the percentiles. 10th percentile at 18. A quarter of the subjects were over 23. Half of them were over 31. And so forth. 10% of them are more than 43 years old. If you add the range from here and here, you've got a 7-number summary with the min, max, and the traditional quartiles and 10th percentile and so forth. Another command for looking at numeric variables is the summary or sum command. Again, you type it out with a space, and then you can enter as many different numeric values as you like. Excuse me, numeric variables as you like. We'll put in the same 2, and what you can find is, again, there's 250 observations. There's none missing. The mean is the same mean, the same standard deviation that we saw on the other 2, and the same min and max. So this one is more compact and contains data that is a subset of the more detailed data you get with Codebook. One of the interesting aspects of this one is that it has a detail option. So you type in summarize whatever variable, age, with a comma, and then you add the options. And in this case, the option is detail, or you can also use DET. And what you get is, again, the name of the variable. Over here is the number of observations. Again, the mean, the standard deviation. You get a few others, statistics, the variance, skewness, and kurtosis. Over here, you get the percentiles, but not just the 10, 25, 50, 75, and 90. You also get the 1, 5, 95, and 99. So we've got a lot of detail, plus the 4 smallest and 4 largest values. And that's particularly interesting because over here, this age of 125 is certainly distressing. We weren't expecting human beings to have an age that high. And what we see here is that there's 2 that are higher than all the others. And that really is a clue that we'll use to clean up the data in just a moment. Well, what about categorical variables? You can you could look at categorical variables if you don't have too many values. So if you've got a binary, perhaps gender or vital status, alive or dead, that's pretty easy to just look at a small table. But if your categorical variable is, say, zip codes or some other marker, voting districts, you're going to have a very long list of possible entries. The thing you want to do here is try and sort out if all the values mean what you think they mean. Do they mean what they should? Sex and state are categorical data in this data set, so let's see what we can do there. Codebook, sex, state, and now this is the same codebook we used before in numeric variables, but this time sex is a string variable of length 6, but there's only 2 values to it. 127 with the text string female and 123 with the text string male. There are none missing. State is also a string variable. This time it's 8 characters, and there's actually 4 unique values. There's one missing, and the missing shows up as the null value or a zero length string. 106 New York, 141 Vermont, and 2 from the state of Vermont. So that looks to be an error that we're going to want to clean up when we get an opportunity. Another thing we can do here is tab the state, and what we see is, again, 106, 141, and 2. The bonus you get here is it calculates the percentages for you. We might want to also include as an option missing, MIS or MISSING, and then the one entry that doesn't have a state will show up with a blank there. Oh, don't forget about graphs. You can use them to look at your data, as you know, and get all sorts of insights, including the data cleanliness. For a continuous variable, a histogram is a good way to go. So let's take a look at a histogram of age, and the command here is surprisingly histogram age. And there we go with a histogram. The data run from somewhere below 20. This is that case of someone who's 125. A little bit distressing. Also, you note that the width of the bins here is 7.3 years, which is kind of an odd and wide number. We can page up once, recover that command, histogram age, do comma width of the bin, and then parentheses 1. And now we get to see individual values of years. And now we can see that there's 2 values, this 125 and this one, which I believe is 52 years old. And it's starting to perhaps give us some ideas about how we got these errors. For instance, this one might just be a typo that should have been 25 years. And this one might have been an inversion. 52, maybe it was really supposed to be 25. Another thing we can do is draw a box graph, box plot. This command is a little different. It uses the general graph command with a subcommand of box and then the name of the variable. Let's take a look at what that does for us. And here we see we've got some people as far down as 0. The median is about 52,000. And we've got an upper quartile of around 75,000. And then starting around 140,000 or so, we've got, looks like about 4 big high outliers. And you have to wonder, are those data entry errors? Well, you know what? Probably not. That's probably just the way the distribution of income is in the world, where most people are relatively low, and a few people have much higher incomes. So that really doesn't strike me as something to worry about as an error. Another way to say this is because I know something about income. I have some knowledge about the nature of the variable. I can make these kinds of judgments. So when you're a data analyst, it's very, very helpful to understand what kind of data you're dealing with, where did they come from, and so forth. Well, let's get down to specific cases and look at individual records. One way to do that is with the list command. Lists all the variables for all the records, and that could be a lot of input. It's the, a lot of output. That's just a simple list command, and there's every variable for record 1, and then every variable for record 2, and every variable for record 3. And every time I hit the space bar, I get another 4 or 5 records. And this could go on a while. It's a little bit overwhelming. So I'm going to hit the break key, and I'm going to say, well, let's just list some of those variables. Let's list patient ID. Now I could type patient ID, or I could go over here and click on the variable to get it to go into the command line. So I want to look at patient ID. I'd like to see their age, their state, their sex, and their income. And now I hit return, and now I've got a little more tractable list, although it's still going to go on for 250 rows. But we can see the first case is a patient identified number 83. They're 42 years old. They're from New York. It's a female. Income $69,401. So rather than let this scroll on some more, I'm going to hit the break command, and I'm going to say I just want to look at the first 20 records, say, the first 5 records. So I'm going to page up, find that same command again, list the 5 variables, and then at the end I'm going to add the modifier in 1/5, and now I get just 5 records. And maybe I would like to look at some records from the middle, maybe 120 to 130, the 10 records in the middle of my list of 250, and there they are. So that's a pretty handy method. Another method that you might want to use is the browse command. It's a spreadsheet view, and that means it's scrollable and filterable, and that's a pretty handy thing to do. There's a bunch of ways to get to browse. You could type in the command browse, or you can go up to this data editor window with a little magnifying glass. That's the browse. And what we have here is each record is in a row. They're all in columns, and you can grab the scroll bar and scroll around. You can find something interesting, like, gosh, most of the races are entered as white and black, but we see an occasional Asian. And then down here, I think I saw one that, oh yeah, that one's obviously a different category. And we can also see some missing values in, for instance, here's the person who doesn't have a state. And various things. You can see the zeros. Sometimes just browsing around is a useful way to eyeball the data and get an idea of what you have. You can also do filtering using this kind of standard filter. You can say, well, I just want to browse people who are female or something like that. You can also say, I only want certain variables to come up on the list. And that's a handy thing to have. Now let's turn our attention to the if statement. If returns the number 1 if the statement is true, or a 0 if it is false. This is a key idea that is worth repeating. A statement that is true is the same as the number 1, and a statement that is false is a 0. How does Stata decide if statements are true or false? Well, it uses your classic logical operators, such as greater than and less than. So if you type in if age greater than 17, all the records that are 18 or older will be marked true with a 1, and all the ones that are 18 or younger are going to be marked with a 0. And you can use greater than, less than. You can use exactly equal to, and let me emphasize, you need 2 equal signs if you're doing a logical comparison, just like you need a greater and equal or a less than or equal if you want to use that concept. You can also use the Boolean operators such as and. If the record is female and from New York, please do so and so. And the symbol for and is the ampersand. That's the one that's over the number 7 key. You cannot type the word and. It also has the idea of the or command. So or is the pipe or vertical bar, which is over the backslash key. You cannot type the word or. And you can say, show me everyone that is in this category or that category, and you'll get a bigger list. There's also 2 ways to say not. I want everyone who is not from Vermont. We could say squiggle not. And that tilde sign is to the left of the number key, of the number row on the keyboard. And then another not is exclamation not or bang not, and they both work the same way. And finally, you can use parentheses if you want to do an operation in first before another operation happens. That's sometimes important for logical operations, much as in high school algebra. The strong thing about if is that you can use it to subset your data. So let's start by tabulating the race category and take a look at what we have there. And here we've got our racial breakdown. We've got 4 categories. 2 records are marked Asian, 26 black, 1 Native American, and 221 white. And there's a total of 250, so there's no missings. Now, this is all comers, but maybe we need to understand what is the racial breakdown if they're greater than age 18. That one is going to have slightly different numbers. And when I hit return now, I see, well, I now only have 223 records. So 37 children or younger people were taken out of the data set, and we can see the racial breakdown for that group. Now we can combine these commands. What if we want to look for people who are over the age of 18 but not too old? They have to be below 25. Perhaps we're looking for something like college age people. So I once again used the page up command, although I could have also clicked over here and gotten it. You just double click on any of these and out of this command history window, and that's pretty handy. Tab race if age is greater than 18 and age is less than 25. And now we're going to get a different count. Now we're down to 50 people, and we've lost our 2, well, we lost 2 of the categories. There's no records marked Asian and none marked Native American left. And what we have here is just the folks who are 19 through 24. It can get arbitrarily more complicated. We could do tab if their age is greater than this and less than that, or forget about their age, maybe they're a student. So what we're looking for perhaps are people who are student age or actually students. So let's try that one. This time I'll go over to here, double click on that last command, rather single click on that last command, And then I'm going to edit it by putting in those parentheses. That means first sort out all the ages, and then say, or the employment record is exactly equal to student. And since it's a string, I've put it in the double quotes. Now we're up to 77. When we did the and age 25, we lost, and less than 25, we lost quite a lot of records, and we're at 50. But now when we add an or command, it goes up to 77. And this is a good time to stop and think about, why does an or expand your sample size and an and restricts it? And that's a general rule. It pretty much always does that. So try to work that out and make sure you understand the way that and or interact. If statements can be confusing, but they really are the key element of programming, and it's important that you get good at them and that you practice them. The next command I want to talk about is a sort, and you can sort your database, your Stata file, by typing in sort and a variable name. So let's sort on inches, and it did it, although it doesn't show it to you. But let's list. Well, you know what? Let's go back and list. We have a nice list command up here. But instead of income, I'm going to put in inches. And let's just look at the first, well, I don't know, how many shall we do? Let's say 20. And what we see here is that the first record is someone who's 57 inches, followed by a 59, and then a bunch of 61s, a 62, and, well, that's the first 20. So these are in order, starting from the smallest number and going up in order. All the other variables for these records are in an arbitrary order dependent on what the inch value was. So all the variables get sorted at the same time. The first thing that we talked about is that sort puts low values first, and it puts numbers that are missing, numeric values that are missing at the end, but it puts missing strings at the beginning. Finally, duplicate values, as we saw, all those 61s, they get put together. Now you can even do double sorting and sort by by two variables at the same time. Let's give it a try. We'll sort by height and then weight. So sort inches, and I believe pounds is next. And I'm scrolling up. Let's add pounds to our output, and again do the first 20. And what we see here is, well, there's only 157, there's only 159, but this whole block of about 10 people with a value of 61 inches, they're in a different order than they were before. They're in the order of pounds. So the thinnest or the lightest person, who is 4'11", excuse me, is that 5'1", I should say, is here, and then the next 120, then the 129, the 142, and so forth. And then when it goes to the next height from 61 to 62, the pounds ratchet back down to 138 and 142, and 150 goes back up again. And it'll do that through all 250 records. Okay, I mentioned missing values. Let's talk about them a little bit more. Stata uses a very large number inside the computer memory to represent missing numbers, and it will display a missing numeric value as a dot or a period. Missing strings, on the other hand, are represented as a zero length or null string. So that is basically the quote marks with nothing between them. They're right up elbow to elbow there. Most commands in Stata know to ignore values that are missing, but one exception to that are the if statements. If does consider missing values. So count if age is greater or equal to 18 doesn't necessarily give you the same value as count if age is greater or equal to 18 and age is less than missing. If you have any missing ages, you will get a different count here. Count if age greater or equal to 18 says there's 234. Count if age greater or equal to 18 and age is less than dot or well, we don't have any missing values. It would also be equal to dot. Excuse me. Not equal to dot. We mentioned missing values earlier. Let's talk a little bit more about how Stata handles them. Stata handles missing number values by assigning a very large number to represent those missing numbers. Stata, this is a number that is so outrageously large, you'll never need to use it in your calculations. Stata displays a missing numeric value, therefore, as a dot rather than showing you the arbitrary large number it uses. That dot is like a period. There's no spaces necessarily. Missing strings are represented as a zero length or null string. That's again, these quotes are elbow to elbow. There's zero space between them. Most commands in Stata know to ignore values that are missing, but one exception is the if statement, which does consider missing values, and that turns out to be handy. For instance, the count command tells us how many records meet the criterion. Let's practice with count a little bit. If we just tell Stata to count, it tells us how many records are in the data set. There's 250. If we say count if, say, BMI is greater than 40, well, we discover there's 5 records with a BMI greater than 40. But we know that very large that a very large BMI number is used to represent missing BMI. So count if BMI is greater than 40, but also BMI must be less than the missing value or dot. And now there's 4. From that I deduce we have one missing value. Another way to get at this would be to do count if BMI is missing, exactly equal to dot. And there's the answer, 1. Finding errors. So let's talk about how to use if statements and the like to come up with internal logic tests that we can use to find errors. The basic idea here is that some combinations of data just don't make sense. For instance, men who've been pregnant. It's very suspicious data. Events that happen after death or before birth are also probably not what you think they are. 2 events that occur to the same person at the same time, but in very different places. Also, very suspicious for an error. So our strategy here would be to count all the records that have these wrong combinations and hope for a 0. But if there is more than 0 such records, then we can look at them and try to figure out what's going on. So for instance, we've got a variable that called pregnancies, which represents how many times the subject has been pregnant. And we have another one, sex, which is a string representing their gender. So we can look at that combination of more than one pregnancy and see if how many of these subjects are male. Now, what I want to remind you about is the grammar here. Count is the command, and that's a verb. And the if statement, which is this whole part from if through the end of the line, is an adverb, if you will, that modifies the command. So if is one of the modifiers. For each record that this, when we run this command, for each record, it's going to say true, or 1, if their pregnancies is at least one or more, and the sex is male. That means that all women are going to get a false. It also means that all people who have never been pregnant are going to get a false. Let's give it a try. Count if pregnancies is greater than 0 and sex is exactly equal to male. And spelling matters in these text strings, so it's important to capitalize M here. And we've got somebody who has a pregnancy count greater than 0 and a sex that is male. And that's a little distressing. We can actually, since we know there's only one, I'm going to go up and edit that command to say list the whole record. And what we have here is it's patient number 13. They make $96,000. They have 10 years of education. They don't smoke. It's a 17-year-old, apparently a man from Vermont, who is employed full-time and apparently has had 2 pregnancies. We know the race, weight, height, and body mass index as well. So the fact that we have their patient ID, hopefully this is linked to other data and we can go back and find out if they are what the story is. There's at least 2 major possibilities. One is that they're not actually a male, and the other is that they've never actually been pregnant. The error could be in sex, pregnancies, or both, to be honest. And I would like to know which one before I decide what to do with this record. Another strategy for doing this would be to use the tab command. And tabulate has a 2-way possibility. So instead of just tabbing pregnancies or just tabbing sex, we can tab 2 variables at the same time. Let's work with that a little bit. If we tab pregnancies, we discover that people have reported between 0 and 4. 2/3 of people have never been pregnant. 32% report 1 pregnancy. 6 people, which is 2.5%, have had 2 pregnancies. Similar number have had 3 pregnancies, and 1 person reports 4 pregnancies. We can tab sex, and we've seen this before, 127 and 123 cases. But if we tab pregnancies and sex, now what we discover is everyone who had 4 pregnancies is female, likewise for 3 pregnancies, likewise for 1 pregnancy. As expected, the 0 pregnancies is mixed with men and women, but the 2 pregnancy line, those 6 people, one of them is a guy, and this is the case that we were looking for before. So tabulating is, like the if statement, is a way to look at your data and decide if you've got a problem. There's other ways to make subsets. We can use the by prefix. The grammar of by is it's a prefix with a colon. So you do by a variable name, you do this command. And it repeats the command for each value of whatever's in the variable. There are other ways to make subsets. Let's take a look at the by and by sort prefixes. Here's the grammar. It's a prefix, so it goes before the command with a colon, and then the name of the command. Although, as a rule, using the variation of it, that the by sort command is usually better. And both of these will repeat the command for each value of the variable. So, for instance, by sort sex, colon, summarize age, will give us an estimate, will give us a summary of age for each kind of sex. Let's give that a try. By sort sex, summarize age. And what we have here is it by sex, it puts all the females together, and it says, oh, there's 127 of them, and here's the summary. 30 years, standard deviation, min and max, and then it just does the same exact thing for cases that are male. The difference between by and by sort is that by assumes that the data are already sorted on the variable of interest. By sort sorts it itself. You can sort by more than one variable, and again, by or by sort will repeat the command for each combination in there. So we can summarize age by sex, but also by combination of sex and smoker. Let's give that a try. I will go over to the command picker over here and click on the recent command, and I'm just going to insert smoker. Well, it turns out there's 2 categories of smoker and 2 categories of sex, so we've got 4 possible outcomes. Women non-smokers, there's 67 of them who are 29.8 years. Female smokers, there's 60 of them, and here's how old they are. Male non-smokers, 56 and their age, and male smokers, 67 of them and their age. And these combinations, these commands, can be quite complex. You can do by sort sex, for instance, and then summarize age if this age or that age, or they're employed as a student, and you can ask for the summary in detail. This / here is handy if you are going to wrap around to a second line. That's the continue on the next row or the next line indicator in a Stata do file. How about correcting errors? Well, one command is replace. For instance, we had that record that was should have been age 25, and I determined that that was record number 198. So we can, ID number 198. So we can replace age equal 25 if ID equal 198. Well, let's list if patient ID is equal to 198, double equal, and what we see here is this is the age with 125. So what I'm going to do is replace the value of age, and I'm assigning it a new value, so it's not a comparison, it's not a double equal, and it's if patient ID is exactly 198. And it made one change. I page up and say list that record again, and now the 125 has become the 25. So that's nice. You can also use the in command if you know what row it is. We could have done replace age equal 25 in, this happens to be record 181, so we could have done that. Of course, it's already been changed, so no real changes were made. You do have to make sure the data are sorted so that the target record is where you think it is. Here's another thing that we can do. We can replace values with an if statement that identifies which actual values we want to replace. So here's the situation where we had that a handful of records that weren't spelled correctly. The state had a typo in it. Let's try and fix that. As you might remember, there's 3 values, but these 2 are wrong. Well, let's replace any state values, change them over to a correctly spelled Vermont if state is exactly equal to Vermont. And again, notice the typo. I had to carefully reproduce the typo. I hit return. 2 real changes have been made. That's good. That's the number we were anticipating. And I run the tab state command again. And now instead of 106, 141, and 2, I've got 106, 143. And that's what we wanted. Another possibility is the race issue. So we've got our race, it's got these 4 categories, and we may decide that we don't want to have 4 categories. Let's create a new variable, perhaps race cat, and let's make it equal to race. And now let us replace race cat is equal to other if race is exactly equal to Asian. Okay, so now when we tab race and race cat, what we see is there's no Asians in race cat. They've been renamed others. The old variable race. The other thing I want to do is I want to change the Native American to on a similar basis. So I am going to page up and change the word Asian to Native American. There's the one change. Now I'm going to go back up again and do my tab and see, instead of Asian, Black, Native American, and white, I've now got black, other, and white. And that's what I wanted for race cat. Now I could have done that in place by changing race, but race, I might want to go back and know which of these others were Asian, Native American, and what. So I am keeping race and now created a new variable. And you can see that over here in the variable list where race is here, and then the last one that I created is at the bottom of the list, race cat. Another option is the recode command. Let's take a look at pounds. And when we look at it in detail, what we see is it runs from the 92 pounder. We have the 98 pound weakling over here. A median of 158, an average of 164. But you look at the 4 largest, and 2 of them just look like folks with pretty big weights, but 999, that is a very high weight. And you might remember that the software program that you got these data from doesn't use the dot convention for a missing value. it assigns it 999 is the missing code. So we could do replace pounds is equal to dot if pounds is exactly equal to 999, but there's another way to do it. So let's skip that one and let's say recode pounds 999 goes, make it equal to a dot, and does it with a shorter command. And now when we summarize pounds in detail, we've gone from 250, there's 248. Our largest one used to be our third largest one, and the mean has fallen from 164 to 158, and that makes sense. Unfortunately, you can only use this on numeric values. Okay, next commands that I want to talk about are drop and keep. Now, drop has two forms that do related things. Drop can drop records, and it'll do that if you say drop if a record meets the following criteria. So drop if age greater than or whatever. You can also drop in number/number. So you can drop in 12, drops record number 12, or you can drop in 12 through 16, and that'll drop 5 records, 12, 13, 14, 15, and 16. You can also drop variables, and you could say drop race and drop race, age, sex, and income. Those are all possibilities. Finally, the command keep does the opposite of what drop does. So everything that keep, if you say keep if age less than 18, well, it drops all the adults. It also notably drops records with missing age because they have an age greater than 18. Okay, next topic is duplicate records. The duplicates command can find records that are identical for some or all variables. It's handy for cleaning up messy combinations of data sets. There's a bunch of options on it. Duplicates can list, tag, or delete records. The delete command, you can make a mess, so be careful. And here's an example. Duplicate, you can shorten it to dupe. Put a tag based on, and the tag, if any records have a duplicate patient ID, and then you need an option, it's a required option, generate parentheses dupe tag. I find this command hard to remember the grammar. This is one where I particularly like to use the menu. And it's on the data menu under utilities. So I go up here, I find data, I find data utilities, and I go over to here, and down at the bottom is option, the 3 flavors of the duplicates command: reporting and listing, tagging, and dropping. Okay, module 3 assignment. What we want to do is make a do file that reads in the file module 3 assignment.csv. You should be able to find that in your file area. I want you to please look for errors, correct them as appropriate, and this is all done with Stata commands. Show descriptive statistics and graphs of each variable as appropriate, and save your new data set as module 3 assignment.dta. And then you'll bring your finished script to class on Monday. So I just want to spend a few last moments showing you how to build up such a script. So here we are back in the Stata window. I'm going to go to the do file editor, and I'm going to open up a new do file. And I am going to make this a little bit smaller. So what I'm going to do here is find the commands that I like, for instance, use. And I'm going to copy it with the Control-C command, or with the right-click, copy it. Then I'm going to go over to my do file editor and paste that command in, hit a return. Then I'm going to do all the other commands that I might want. For instance, maybe the next thing I want to do is probably go a ways down before we did any that we actually did corrections on. Here we go. I'm going to be replacing that. I'm going to be replacing that one. And you can, in fact, using the Control key, I've highlighted row 52, 55 and 56, 58, 61, and I can copy all of them in one movement and go over here and paste them in. And then I can add the other commands I want, the tables, graphics, whatever else I want to add. And I can then add the save command, which you already know how to do, I think. So, and then save this file as, perhaps module3.do, and bring that file to class. I look forward to seeing you on Monday. Thank you.